So we will continue our discussion with filters, and in a previous class, we were looking into few concepts where we saw how or what type of filters these are. Okay, what is a notch filter, and how the signals are going to be. Okay, the stop band, right? So all that we actually looked into band pass, then the high pass filter, right? So which actually passes only the high frequency signals, and the low frequency signals are attenuated, right? So these were some of the things which we actually looked into. Fine. Now, based on the types of rate of fall, also we have discussed, right? 20 dB is with respect to first order, 40 is with respect to second order, and 60 is with respect to third order. So the way in which they fall is actually, more steep as the order increases. Fine. Now we need to know some basics about it, right? Capacitive reactance is one such important term, which is XC. Okay. So capacitive reactance is inversely proportional to frequency, so which is 2 pi fc, 1 divided by 2 pi fc. One important thing is at low frequency the capacitive reactance is high, right? So please make note of this. At lower frequencies we find that the reactance is very high, and at high frequency the capacitive reactance is very low. Okay, so so you can see that they are actually inversely proportional. Right now in circuit, okay, now the circuit that you can see here below, if XC is very high, okay, so usually at high frequency, okay, the capacitive reactance will be small, so it is like inversely proportional. So then the entire voltage VI will come across XC, therefore V naught is equal to VI. So if the if the capacitive reactance is very high, okay, so if it's high, okay, then you should consider the first case here. When the capacitive reactance is high, then it is actually operating at lower frequency. So frequency reactance are inversely proportional, keep in mind. Okay, so you can understand that by this formula actually, right, where frequency is at the denominator at the right hand side, and your reactance is at the numerator side with the left hand side. So they are inversely proportional. So when one is increased, the other one will decrease, right? So that's an important factor to be remembered. So as XC increases, my frequency will reduce, right? Now if XC is very small, which means at higher frequency, then the entire voltage drop is across R1. So whatever voltage that comes will be dropped across this R1. Okay, so I will not get the output voltage, which means my output voltage is going to be 0. So if I want my output voltage to be equal to input voltage, then I have to use XC to be very high, right? XC should be very high, which means it will be operating at lower frequencies. So these are some of the conditions that you got to remember, right? Okay, so we also saw this first order low pass filter, right? So but then we'll just look into it. Now this is a passive low pass filter, okay, having the input resistance, capacitance, and the load impedance and the output voltage. Now this part, this part becomes the passive, okay, and this part becomes the part or the summing part, right, where we have, or an active part, right? So this is a passive part and this is an active part. Why do I call it as an active part? Because it has the op-amp in it. Okay, so in passive filter, load will affect the filter performance. So whatever load is there, okay, that is actually mainly dependent. So to isolate the load, we use an active element, right? So what is that active element? It is nothing but an op-amp or a transistor. Now the voltage gain, as we all know, it is output by input. So this is XC1 divided by R1 square plus XC1 square. So make a note of this formula, right? You will be needing it for solving problems. Now, at low frequency, the capacitive reactance is very high. So we know this point, right? Lower frequency, the capacitive reactance is inverse. And therefore, the entire voltage drop is across XC1. Okay, so which means when I have a lower frequency, okay, my capacitive reactance is high. So if my capacitive reactance is high, then whatever is the load, right, so that will be coming across the C, right? Therefore, there is a little attenuation of the signal. Why is this a little attenuation? Because the capacitor can fully charge and keep it along, right? At high frequency, the capacitive reactance is very low. Therefore, entire voltage drop is across R1, right? So this becomes too low, and the dominant one becomes the resistor here. So whatever is the input, there's a drop here, and output voltage will not be equal to input voltage, and there is full attenuation, right? Just like the one we saw previously, those two conditions, right? Where if I want V0 is equal to Vi, I need to make sure that Xc is very high. If Xc is very small, then output is equal to 0, which means there is a lot of attenuation, right? Now this is going to be the graph for the first order filter. So as I was mentioning, it has a 20 dB fall, right? So this is our low pass filter, because this is a pass band region, and then it gets into a transition band and then stop band. Why is it transition? Because it's moving from a high value to a low value, right? So since it's moving from a higher value to a lower value, we term it as transition band. And then it is in stop mode because there is nothing there, right? So stop band, transition band, pass band. Okay. Now gain versus frequency and phase versus frequency is shown here, right? So you have AV, okay, which is the gain, and you have 20 dB per decade, so that's also shown here. And this is our cutoff frequency, right? So this point at 100, okay, at 100 hertz is our cutoff frequency. At low frequency, gain is constant with small insertion loss. It is called passband. So as I told you, passband is something where there is very minimal loss. Then attenuation band is divided into transition and stop band. So from here, okay, let me just show you. So from this section, okay, to this section is what is called the attenuation band. Okay, so that whole thing is the attenuation band. Okay, so this full thing is attenuation band, right? Okay, and at cutoff frequency, okay, now the gain falls by 3 dB. So at 3 dB, you find that it is actually falling down. In transition band, gain is attenuated with fall rate of 20 dB. So now remember, if it's a first order, then it's going to be 20 dB. Okay, and in stop band, the gain is totally attenuated. So I do not have any gain in the stop band. So it's totally coming down, isn't it? So this is my transition period, right? This is my transition, and this thing is my stop band. So in stop band, what is happening? I do not find any gain. The phase angle between input and output is actually 0 degree at lower frequencies. So at lower frequency, there is no angle because it is constant. Okay. Phase angle between input and output is minus 45 degree at cutoff frequency. So at cutoff frequency, there is an angle that gets created, right? And phase angle between input and output is minus 90 degree at high frequency. So it just falls off, okay, when there is a increase in frequency. So the cutoff frequency occurs when gain is at 3 dB, or I told you 1 by root 2, which is 0.707. So this happens, okay, when XC1 is equal to R1. So my FC is going to be 1 by 2 pi R1 into C1. So this is also an important formula here, right? Where I'll be using this value to calculate the capacitive frequency. Okay. Fine. So students, up till this point, do you have any doubt as to how this graph looks? What is this minus 3 dB? What is this gain? What is attenuation band? What is pass band? What is transition? What is stop band? Are you all clear with this concept?
Yes, sir.
Okay, fine. So the only thing now you have to do is, note down the formulas, and it will be easy for you to solve problems. So there are a few design steps now. Okay, select C1 very much larger, okay, than the stray capacitance. Okay, so for example, I'm going to select C1 is 1000 picofarad. Okay, so very large C1 I'm going to select. Why are we doing that? So that the capacitive reactance is high and there is no loss, there is no attenuation, and output is equal to input because everything is stored at the capacitor. Then calculate R1 using the equation. So what equation I'm going to use? The same thing, that we discussed previously, which is nothing but FC is equal to 1 by 2 pi R into C. Okay, and we will be using R2, okay, same as R1. Okay, so where is this R2? R2 is actually connected here as the feedback, right? So this is my passive part and this is my active part. Okay, so R1 value will be made equal to R2. So keep these 3 points in mind and we can design any low pass filter. Now, using 741 op-amp, design the first order active low pass filter to have 1.2 kilohertz cutoff frequency. Now FC is given to us, which is about 1.2, and we need to design a first order, which means I'm going to have one resistor here, first order active low pass filter. So resistor and capacitor. Remember the combinations that I was talking to you about. When these are reversed, okay, what is going to happen? It's going to become a high pass filter. Okay, now I have a resistor here, so it means it's a low pass filter. Okay, now we're going to use this first select one, okay, which is C1 is equal to 1000 picofarad. So this is capacitance. So most of the problems will be actually considering this. So even if I've not given you in the problem, even if it's not mentioned, then you will have to consider it. Okay, and you will have to take this value by default. And we have the value for R1. Okay, R1 is equal to 1 by 2 pi FC into C1. So 1 by 2 pi FC is nothing but 1.2 and C is nothing but 1000 pico. So when we try and multiply, right, we get this 132 kilo ohms. So we do not have the standard. So we'll be using 120 kilo ohms. Okay, so it's fine to use standard values, right? Okay, so the next thing, I have calculated FC. FC R1, yeah, R1 I have taken here and FC I have taken down. Fine. So this is done. So the next thing is I need to maintain R2 is equal to R1. So which means my R2 and R1 both are how much? 120 kilo ohms. So for 120 kilo ohms, we again calculate what is going to be the value of C1, because we need to get the practical values, right? So C1 is equal to, okay, 1 by 2 pi FC into R1. Okay, so 1, 2 pi, and FC is 1.2 and R is 120. Okay. Fine. So using this formula, I found out what is R, and I'm going to send this R and get the R bottom, so that I'm going to get the value of capacitance. So that is going to give me about 1105. So I'm going to use the standard 1100 picofarad. So the main thing that we are actually doing here is calculating what is going to be the value of R1, calculating the value of R2, and finding out what is going to be the value of C. Okay, so these are important, and of course the FC is going to be given in the problem, and we are going to assume temporarily the value of C, right? So any doubts in this problem, students? Able to follow? Simple, right? If you have the formula, just substitute and get the values. Any doubts here in this problem?
No, sir.
Okay. Next, we will move on to the other concept, which is high pass filter. Okay, so as I mentioned, what is going to happen here? There's going to be a change. So resistor is going to come here and capacitor is going to come at the top. And I have my input voltages. This section remains the same, right? Which is the active section along with the op-amp, right? And rest of the things are now the formula does change, right? R1 AV is equal to R1 divided by XC square plus R1 square. So you have to note down these formulas, right? So that you can use it for your problems. Okay, fine. Now at low frequency, the capacitive reactance is very high. So the same concept continues, right? We're not deviating from that concept, right? And we are seeing that at high frequency, right? At high frequency, the capacitive reactance is at low frequency, the capacitive reactance is very high. Now, one more thing I wanted to tell you was, this region is also acting like a voltage follower. Okay, and this is a passive filter. Okay, so let me just annotate that. Right, so this is the passive filter. Okay, and this section is going to be the voltage follower. Now, can you tell me what is a voltage follower, students? What's a voltage follower?
Output voltage follows the input.
Right. So whatever voltages are there at the output, right? The same thing is actually appearing at the input. Now, why do you think this is happening? Because it is connected to the positive terminal. So there's no inversion. So there's a non-inverting configuration, right? So we can also call it as a non-inverting amplifier, or we can even call it as a voltage follower, right? So yeah, keep this in mind. Fine. At high frequency, the capacitive reactance is very low. Therefore, entire voltage drop is across R1. Therefore, zero or minimum attenuation. So at high frequency, now this is going to be a reverse here, a reverse in concept, right? Low frequency, capacitive reactance is high. That is fine. Okay. But what is happening when capacitive reactance is high? There is an attenuation happening. But in our previous case, in our low-pass filter, we saw that when the capacitive reactance is high, there used to be no loss, right? Now, at high frequency, the capacitive reactance is very low. Now, that is common for both low-pass and high-pass, right? But the only thing changing here is, the part where it says, with regards to attenuation. So, attenuation is high and attenuation is low when the capacitive reactance is high and low. So you can think of both low pass and high pass acting like opposite to each other. Okay, and this is an important formula for you to note down. Okay. Next, now what is going to be the characteristics of this? At lower frequencies, there is going to be a transition period. Okay, so I can call this as a stop band, okay, a transition band, and then pass band, right? So at lower frequencies, there is a you find that the output is actually climbing up and trying to become stable, and from here, okay, after the FC is when it starts becoming constant, and it's called pass band, right? So gain versus frequency is shown. Okay, gain versus frequency, and then what is happening to the angular form, right? Plus 90 and plus 45, and at 0 degree, what is happening. Then at high frequency gain, Okay, at high frequency gain is constant with small insertion loss, but this happened in reverse with a low pass filter. So low pass filter, here it was constant and then it slowly came down, but then in the high pass this section is getting attenuated and here it's getting constant. Attenuation band is divided into transition and stop band. Okay, here you do not have to show about the transition band. You can just talk about generally the attenuation and pass band, whereby previously you can see that there was transition band and there was stop band. Okay, so here you can just talk about the attenuation and pass band. That should be sufficient, right? So you can also see here that in the first order active high pass filter circuit and frequency response graphs, okay, the -3 dB cutoff frequency occurs when XC1 is equal to R1 and gain is falling at how much? 20 dB per decade, right? So the fall is about 20 dB. Okay, let me just go to the high pass. Yeah, so the fall is also about 20 dB. Okay, right. In stop band, the gain is totally attenuated, so that's why it's called stop, isn't it? The phase angle between input and output is 90 degree at low frequency. So at lower frequencies it's about 90 degree. Okay, and the phase angle between input and output is 45 degree at cutoff frequency. You can see that this is the cutoff frequency, so 45 degree angle has been created. Okay, and the phase angle between input and output is 0 degree at high frequency. So at high frequency there is no angle that is actually forming, so it becomes parallel. Fine. So the cutoff frequency occurs when gain is at 3 dB. This happens when R1 is equal to XC1. So the formula here is going to be FC is equal to 1 by 2 pi R1 C1. So what was our previous formula? Our previous formula also was the same. FC is equal to 1 by 2 pi R1 C1. So we are going to use the same formula, but then the structure is going to change, right? R and C both are interchanged. Okay, fine. So what are the design parameters here? Select C1 very much greater than stray capacitance. So as usual, we're going to use the same 1000 picofarad even here. Okay, and we need to calculate R1 using FC is equal to 1 by 2 pi R1 C1, right? And we're going to equate both the resistors. So pretty same the design way in which we do for LPF and HPF, low pass filter and high pass filter. Let's see a problem, a simple problem. Using 741 op-amp, design the first order active high pass filter to have 10K cutoff frequency. So cutoff frequency is given here FC, and we need to design the filter. So designing filter is nothing but calculating the R's and C's, right? So C, I'm considering it to be 1000, and I'm going to interchange R and F here, right? R is going to come here and F is going to come down. So 1 by 2 pi FC into C1. So I'm going to substitute the values 2 pi FC. FC is what? 10K. 10K is substituted. C is selected at 1000, right? And it should be giving me about 15.9. So 0.9 I will eliminate, okay, because I'll be using a standard value which is 15K. Okay, fine. So the problem seems to be pretty simple. Now we will move on to the second order. Now in second order, the difference that you can see here is I have an extra resistance. Let us go back. Let us go back. Right. So here I just had one resistor, one capacitor, and a resistor across my feedback network. I didn't have any capacitance in the feedback network. Now in the second order, I am having a positive feedback also, and that is I'm having with respect to via capacitor, and I have a resistor in the negative feedback network, extra resistor, right? So this is making me call the circuit the second order filter. Okay, so what is the second order filter? Okay, it's a two-pole filter. Okay, and it has a fall off rate of about 40 dB as we saw. So as the dB per decade increases, okay, the slope becomes more steep. Okay, that is what you should understand. So we have an extra capacitor here and an extra resistor here, right? So this is a little more complex structure than first order filters. Okay, fine. So the fall off rate, as we all know, is about 40 dB, and at low frequencies, XC1 and XC2 are very high. So frequencies and capacitive reactances are always the same, right? So they are inversely proportional, either low pass filter or high pass filter. Okay, and the input signal are reproduced at output. Okay, so entire voltage will appear across XC1 and XC2 and is almost open circuit. So similarly, how we saw in low pass, whenever the reactance is high, high means low frequency and there is not going to be any attenuation. So for the first order and second order, the explanation or the theory that you're going to write is going to be the same, just that the circuit changes and the fall off rate changes. Next, at high frequency, the reverse happens. The capacitive reactances are small, therefore there is a voltage drop, and there's a lot of attenuation. Okay, and that happens between R1 and R2. So which means R1 and R2, there is a lot of loss that happens. So attenuation is high. Because of the combination C1 R2 section, okay, in the C1 and R2 junction, okay, here, this part, and feedback from C2 to junction R1 and R2, okay, we get a fall off rate of 40 dB per decade. Now the thing that's enabling, okay, now you might ask me, sir, how is this happening? How is that we are able to achieve this 40 dB? That is because of this junction here, okay, and this junction here. So the junction between C1 and R2 and the junction between R1 and R2 and C2, right? So because of this kind of combination, we are able to achieve the 40 dB fall off rate. Okay. So sometimes, to confuse you, I might even ask, write a note on Sallen-Key filter. So Sallen-Key filter is also called as the low pass filter. And sometimes, this is also called as voltage controlled voltage source filter. Okay. Now, why is this called voltage controlled voltage source filter? Because it is having an input voltage, okay, and it is controlled by a voltage source, right? So that's why we call it as VCVS. Please make note of it, VCVS. Okay, right. So this is going to be the graph for it. Okay, we are attaining it at minus 40 dB, right? So the steep that you can see is high. Okay, so at lower frequency, the gain is constant and there is small loss, and attenuation is divided into transition band, right? So you can see all that. And at cutoff frequency, it falls by 3 dB. Transition band is attenuated with a rate of 40 dB per decade. Keep these numbers in mind. It will help you for solving the problems, okay, and to write about the filter. In stop band, there is total attenuation of gain. Okay, that's the reason why it's called a stop band. Then the phase angle, okay, between input and output is 0 and 0 degree at low frequency. Then the phase angle is about 95 degrees, right? And you can actually, it's about 90 degrees, right? And then the phase angle between input and output is about 180 degrees, which means it is out of phase, right? It is out of phase. So this is coming down and this is going here. So there's a huge shift. Okay, so let me just draw. You'll be able to understand, right? So if you can compare, right, between this graph and this graph, there's a huge shift. So it is coming here. So which means there's a 180 degree shift. Okay, so that's why there's a minus symbol there. Okay, not only 180 degree, but then it's going in the reverse direction. So minus 180 degree. The formula here becomes important, which is FC is equal to 1 by 2 pi root R1 R2 C1, C2. Keep this in mind. 1 by 2 pi R1, R2, C1, C2. This formula is needed for our problems. Okay. Fine. Now, what are the design things that we need to keep in mind? Keep this 5 steps in mind. It will be easy for you to summarize and come up or solve the problems. So what I have done here is I have summarized things so that it becomes easy for you to solve. So step 1, as usual, we're going to use C1 is equal to 1000 picofarads, right, which is taken as a standard, right? Even for low pass, we use the same thing, right? And we're going to equate R1 and R2. Low pass also we did the same. Now, the thing that we're going to do here extra is C2 is going to be 2 times of C1. Now, this is important, right? C2 is 2 times of, so this C2 which you are seeing here, okay, which is acting like a positive feedback, not exactly positive feedback, but then the part of the output is taken and it's given between the junctions of R1 and R2, right? So this section, okay, or this capacitor here will be 2 times of C1. Okay, so C1 we are using 1000, so which means this should be about 2000 picofarads. Then R2, okay, find R2 or R1 using this formula. So R2 is equal to 1 by 2 pi FC C1 root 2. Okay, so that is going to be the formula. So if in case it's like XC1 is equal to root 2 times of R2 at cutoff frequency. So XC1 also I can calculate. Okay, then R3 is equal to, so this resistance R3 will be a combination of both R1 and R2. Okay, so whatever is the value here for R1 and R2, I'm going to add that, and R3 is going to be the final value. So keep in mind that this design procedure that you are seeing here, okay, applies to only circuits that use voltage follower. Why is it a voltage follower? Because it's connected to the positive terminal here, right? And it's a non-inverting configuration, and it does not apply to circuits or op-amp which is connected as non-inverting configuration. So for non-inverting, again, we have to deal with all this change in phase. We have to put the minus, so many things different. So usually we go with a non-inverting configuration. Okay, so we'll solve a quick problem here. Okay, using 741 op-amp, design the second order filter, second order low pass filter to have 12 kilohertz as FC, and use the selected components to calculate the actual cutoff frequency. So they're telling us to recalculate the cutoff frequency, okay, using the selected components. Okay. Now, what we're going to do is we're going to select C1 is equal to 1000 picofarad and R2 is equal to 1 by 2 pi FC C1 into root 2. Okay, so 1 by 2 pi FC was given as 12 kilohertz into C we are taking as 1000 root 2. Okay, so that should be giving me about 9.38. Now here I wouldn't be using 4.7 because that would drastically reduce R2. Why I'm not doing that? Because again, R3 is dependent on R2. So because we are adding these values here and then I'm getting an R3, so which means there is going to be a huge change. So I am trying to make it as accurate as possible. So I will be using a combination here, 4.7 plus 4.7. So that should be about 9.4. Yeah, that should give me about 9.4, which is about 0.02 kilo ohms extra. That's fine, right? Then I'll be using the second condition here. I'll be equating R1 and R2. I'll be making both of them same, so which means 9.4 for both. And remember, I'm not taking here 9.38. I'm taking 9.4 because I'm adding them up, right? Practical values are taken. 2 times of C1, which means 2000. So R3 is equal to R1 plus R2, right? So it's like 2 times of this R2. So 9 to 18.8. So I'm going to use an 18 kilo ohms here. Now FC, FC, as we all know, is 1 by 2 pi R1, R2, C1, C2. We're going to use this FC. And so 1 by 2 pi. Okay, R1 we have, R2 we have, C1 we have, and C2 we have. So this is going to be about 11.97. So see, you can see the change, 12 kilohertz, and then now we are getting about 11.97 kilohertz. So there's a slight change in the cutoff frequency. So that's the actual cutoff frequency, right? So there's a difference here, as I was mentioning, right? 12 kilohertz was given, and then when we recalculated and when we saw and we put the practical values, it has actually come down to the cutoff frequency by about 0.03 kilohertz, right? Now the second order high pass filter, okay, high pass filter, it just had a capacitor and a resistor. Now the reverse is going to happen, right? So an extra capacitor and an extra resistor. Now capacitor was here in the low pass filter, and resistor was here in the low pass filter. So we are just going to interchange them with regards to high pass filter. So as we know, it's going to be about 40 dB, the fall off rate, and at lower frequencies, XC1 and XC2 are very high, therefore input signal are totally attenuated. But then in the low pass filter, it was not getting attenuated. So the explanation with regards to first order, second order high pass filters will remain the same, except for the point with the fall off rate and the circuit. Right, and high frequencies XC1 and XC2 are very small, okay, and it behaves as short circuit, passing the input voltage unattenuated to the voltage follower, right? So the reverse is happening here in the high pass filter. So low frequency, high capacitive reactance, so that is in both low pass and high pass, first order and second order, right? Okay, but then with low pass, higher XC, no loss. Lower XC, there is loss. But in high pass, it's just the reverse. Because of the combination C1 and R2, okay, so the feedback from C2, okay, C2 junction of R1 and R2, okay, so because of this junctions here, okay, R2 and C2, okay, and R1 to C1, C2, okay, so we are having a 40 dB per decade combination, right? So we'll just mark it up. So because of this junction here and the junction here between R2 and C2. Okay, fine. And then now we are looking at the same graph here, but then the rate, the fall off rate is actually slightly increased. Okay, so it's at about 40 dB, right? And you can see it's 180 plus 180, 90, 0. Why plus 180? Because it is going here, so there's a shift happening. Let me just draw that, right? So there's a shift happening in this way. So there's a 180 degree shift. So keep that in mind. Okay, so it's a plus 180, and at high frequency, the gain is constant with small insertion loss, and that is called a pass band. Okay, and attenuation band is divided into transition and stop band, right? So this becomes my stop band and this becomes my transition band. So cutoff frequency, it falls at minus 3 dB and 40 dB is the fall off rate. At stop band, there is a total attenuation, right? And the phase angle between input and output is 180 degrees. The phase angle between input and output at the cutoff frequency at this point, okay, at this point is about 90 degrees. You can see here, right? Let me show you. Okay. So take this point here and at this point. right? So you can see that it's about 90 degrees, and the phase angle between input and output is 0 degree at very high frequency. At high frequency, there is no angle that is being formed, right? It's going to be parallel with each other, so there's a 0 degree at high frequency. And the cutoff frequency, okay, the formula is going to be the same, which is 2 pi R1 R2 C1 C2. Okay. So let's try and solve a problem, and we'll have this design parameters in mind before we solve, and it becomes easy for us to understand. So capacitor, we have C1, C2 and R1, R2, R3, the same, okay, the same usual high pass filter that we are using here. So C1 is taken as 1000 picofarads, right? And we're going to use R1 is 0.5 times of R2. Now this is different here. Okay, R1 is equal to 0.5 times of R2, and C2 is equal to C1. Okay, C2 is equal to C1, and we can select R2 by using the equation √2 divided by 2 pi FC into C1. So this is also a new formula. R3 is equal to R2. R3 and R2 both are equated here. So what I suggest is you make 4 sections. First order filter, second order filter. In first order, again, I have low pass filter, high pass filter. Second order also I have low pass filter and high pass filter. Write the circuits for them. Okay, so you will get 4 circuits, and then you can write the design equations for them. Okay, so you will get 4 design equations, 4 different sets of design equations: low pass, high pass, low pass, high pass for first and second order respectively, right? So just before you go to exam, right, you can revise them. See, for example, here in high pass filter, you're using R1 is half of R2, right? So this you should not apply in the low pass filter, right? Okay. Students, you're understanding, right, what I'm trying to say here, right? So if you can write them and keep, it will be easy for you to differentiate between the different filters and the design factors, right? Yes or no?
Yes, sir.
Yeah. Okay. So we'll solve a problem here using 741 op-amp. Okay, design the second order active high pass filter to have 6 kilohertz cutoff frequency. So FC is going to be 6. Use the selected components to calculate the actual cutoff frequency. So it's going to change from 6. So we will recalculate that FC. C1 is taken, right? Then C2 and C1 is 1000. Okay, why is that? Because of this third design statement, right? 1000 picofarads. Then R2 is, we are having the formula √2 divided by 2 pi FC C1, right? So √2 divided by 2 pi, and FC is 6 kilohertz and C is 1000. So I'll be getting about 37.5. Now remember, when we are designing filters, we have to make sure that the values are made constant. Even though we select certain standard values, but then still, right, there shouldn't be so much of difference. See, for example, if I use only 33 kilohertz, kilo ohms here than 37, so that's going to have a huge impact. Say, because R2, and then I'm going to equate R3, right? R2 and R3. So this is giving me a negative feedback. So there's going to be a lot of impact on this voltage follower. Okay, so R2 is about 37.5, and R1 is half of R2. So which means 0.5 multiplied by 37, so which is 18.75. So see, point change in the point is fine, right? 18, and instead of 18.75, if I use 18, that's fine, right? But you shouldn't change it to, from 37 to 33. That's a huge difference. Now R3 is approximately equal to R2, so which means it's going to be about 37.5. So I'm going to use a 39 kilo ohm standard, right? So this is almost equating to 38, so 1 kilo ohm difference, that's fine. And now we are going to recalculate what is going to be the FC, now that I have all the values of resistance, isn't it? So 1 by 2 pi, R is there, which is 19.5 R1. Where is our R1? Yeah, so I think it should be 18.7. Okay, so 18 we are going to use here, and R2 is 39. We have used a different value here, right? Then C1 and C2 is also the same, right? Okay, so 19, okay, 19.75, 19.5, and then 39. Why are we using 39? Because it is here we are using a standard value for the resistance, right? And then C1, C2, both are the same. So we are having a reduction here, which is 5.77 instead of 6 kilohertz, right? So that's about how we design FC. So first you have to know these design conditions. So once you're sure with the design conditions, then you can proceed with the solving of problem. So as I mentioned previously, keep them all together, okay, so that you can actually look into them and see how to design. So in our upcoming class, right, we will be looking into band pass filters and band stop filters, right? So we will just look into how this happening. So we have seen low pass and high pass both in first order and second order. Now the only thing that is left out is band pass and band stop. So we will also be looking into this few concepts in our upcoming classes. Okay.